Greetings. I hope that all of you are doing well today. So we'll have a new session today, and this session will be recorded. So I apologize for that. You know that I have illness and I just do my best to record this session for you today. So let's get started and just remind you guys what we studied before. So we studied Bloch's theorem, and also we studied the periodic potential. We know how the periodic potential work, and also guys, we solved Schrödinger equation and get periodic wave function. What we will try to do today, we will try to do the following, guys. So we will study Bloch, wave function, and boundary condition. So we are going to study Bloch wave function and boundary condition. Okay, so if you try to go back, guys, to the dispersion equation, the equation that describes the energy. So you can see that the energy is function of k squared. Okay, and when we try to draw k squared, that actually will give me parabola, as you can see. So energy as a function of k, so that can give me parabola. In case of a continuous energy, so it will be parabola, but actually here we are dealing with quantized energy levels. So you will see that there is a discrete discrete energy values, and that actually will give me some spaces in this parabola. Okay, so you can have the parabola like this, and then space, and then continue the parabola, and then space, and then continue the parabola again. Okay, since we are dealing with discrete energy levels, so we can draw guys the energy levels like this. We can draw energy as a function of k. So this is a k value and this is a k value, and I will talk a little bit more about these two values, guys, pi over a and pi over a. What is a right here? A is the lattice constant, so we'll talk about the lattice constant. Okay, so you can see that here we can see that we have energy level number 1, and here we have energy level number 2. And what we have in between here, we have something called Brillouin zone. Okay, we will talk about that. We will talk about that a little bit more. So I included that in this session, but I will not talk about that in details. I will just mention to that. Okay, so you know what do we mean by Brillouin zone. Now let's ask ourselves like very important question. I will come here and see the question. So how do we normalize the wave function, Bloch wave function? How can we normalize this wave function? And we know that Bloch's wave function is psi nk as a function of r, the position vector, that's equal to exponential I, the complex number, k dot r u n k as a function of r. What is this u here? The u that we have right here actually is the periodic. This is the periodic function that we include in Bloch's equation. If I try to draw that maybe for you guys, it will be easy to show you that, yeah, this wave function can be like this. Okay, so this is the wave function, and we continue doing that. So this is u of r. Actually, this is u of r. This is the periodic wave function. Okay, and we know that we have here barriers, as you can see, between these atoms. And actually in this figure, just guys, to help you to see that, so we have here atoms or ions, and between these ions there is a constant distance a. So we have 0a, 2a, 3a, 4a, 5a, and then Na. This Na can be any number, maybe 1000, I don't know. I have a huge number of atoms along this horizontal line. So this is considered as an array of atoms. This can be considered as a one-dimensional lattice, that's possible. But I just tried to help you to see that, okay? To see the periodic wave function. Now we asked ourselves this question. That's very nice. And also, guys, we know the energy levels for this kind of system. Okay, so this is the energy levels, guys, for this kind of system. And I showed you guys how the energy levels or the orbitals can be distributed. Okay, can be distributed, guys, along this potential well. Okay, but since we have a periodic wave function and we have one-dimensional lattice like this, so the energy levels should be like this. And I just consider the first level and the second level. I don't need to go deeper, guys. So that's very nice. Let's now move to the other question, or the next question that we need to answer. Let's come here. How to normalize the wave function? So this is one question. So how do we count the number of states? How can we count the number of states? So this is another question that we need to keep in mind. So how can we do that? How can we count the number of states? This is very important. So what's the importance of this of these questions here, guys? Actually, these questions are very important to find the density of states. So there is something called density of states. If we go to quantum mechanics, we will see that density of states can be considered as an operator. Okay, so answering these two questions can help us to figure out the density of states. So this is the first thing, guys. And also that can help to understand the properties of the system. The properties of this system of ions or atoms, this one-dimensional lattice that you can see right here. And again, I would like just to emphasize that the distance between these atoms is constant. And this is actually called the lattice constant. So let's go down a little bit. Let's go down, guys, a little bit here. So you can see the rest. Yeah, so this is what I just mentioned. So answering these questions, guys, so that's important to find the density of states. To find the density of states, and also that can help to understand the properties of the system. So that's why this is important, guys, to be studied. If I go down here and try to answer this question, these questions, how can we answer these questions, guys? It will be easy to answer these questions. So to answer these questions 1 and 2, we do the same idea. So we need to apply the same idea that we used to deal with a free electron. So if you go to quantum mechanics, guys, and try to solve the free electron problem, you need actually to solve Schrödinger equation, and to solve Schrödinger equation you need to work on the wave function, and the best way or the best choice for the wave function is to have plane wave. And you can see that here, guys. So you can see that, just to recap and help you to remember that. Okay, just to help you to remember that. So the wave function, guys, that we used when we solve the free electron wave function is psi nk is equal to c nk exponential I k dot r. This is plane wave. And in 2 dimensions, this plane wave can be considered as psi nk as a function of x. That's equal to c nk exponential I kx. This is what we use, guys, to solve the free electron problem. But we need here to respect something, guys. We need to respect or apply the periodic boundary condition. We need to respect and apply the periodic boundary condition. So the periodic boundary condition, guys, I will define that again. This is what do you mean by periodic boundary condition. You can see that these ions repeat themselves and that continue, and also the wave function repeats itself, so it is periodic wave function, which is Bloch wave function. And you can see here that we have the part that's talking about exponential I k dot r, and k is the wave number, guys. Okay, it has something to do with the number of ions or number of atoms in this one-dimensional lattice, and also has something to do with the length of this array of atoms. Okay, that's fine. And now I will go down a little bit, as you can see right here. And now, guys, we mentioned that this is the plane wave that we use to solve the free electron wave function. And just to remind you, guys, if you still remember the free electron problem, I just will remind you what do I mean by the free electron problem. So if you still remember, guys, one of my early sessions includes solution for the free electron problem. We just consider the free electron inside the box, and then we need to know the dimensions of this box, and we need to solve then Schrödinger equation. When we solve Schrödinger equation, you will see that the solution for this wave function can be plane wave, or you can consider the solution as sine wave. So you can have sine along x-axis and sine along y-axis and sine along z-axis. So you can have psi is equal to normalization constant times sine kx times x times sine ky times y times sine kz times z. If you still remember that, guys, and this is what I'm talking about. So if I go down again, as you can see right here, so I will go now here and try to show you that, guys. So I will move the camera a little bit up, as you can see right here. So that is very nice. So you can see, guys, the plane wave that I talked about right here, okay, and the boundary conditions that I talked about, all of these means that psi nk as a function of x plus na is equal to psi as a function of x. This is the periodicity condition. And the wave function, guys, repeat itself over n unit cells. So you will see that the wave function repeat itself over n unit cells. These unit cells can be in one dimension, so that's possible. They can be in one dimension. If I go up again if I go up again, guys, and move this a little bit to the left. So this is a one dimension. So we have n atoms, as you can see right here. Okay? And the wave function repeat itself over the unit cell. So this is a unit cell, this is another unit cell, this is another unit cell, this is another unit cell, and this is another unit cell, and this is another unit cell, and etc. So we have, according to what I have right here, I have 1, 2, 3, 4, 5, 6. So I have 6 unit cells here in this one-dimensional lattice. So that is very nice. So let's go now down again and go to the free electron problem and the plane wave, and move now to the left. When we normalize this wave function, we will see that C in K actually is equal to 1 over square root n times A. This n that you can see right here, this is the number of unit cells. This A right here is the lattice constant A, and n times A actually is equal to L, and L right here actually is the length of this array. And you will see, guys, that K, this wave constant here, actually is equal to 2 pi over L times n. Okay, this is K. And maybe I need to go a little bit closer so you can see that. So let's do that, guys. So go closer and closer. So let's do that. So like this, guys. So maybe that can help you to see that. So we have 1 over square root n times A, and that's equal to 1 over square root of L. L is the length of the array of atoms, and K is equal to 2 pi over L times n, when n is equal to 0, plus minus 1, plus minus 2, plus minus 3, and etc. So we can have here plus minus 2 and plus minus 3, and etc. Okay, so this is a number, this is a constant. So that's very nice. That's very nice. This is, guys, how do we deal with a free electron? Okay, and this electron can exist, actually, guys, can exist here in this system of ions. So let's go up now. Let's go up. Okay, and then move this a little bit up like this. Okay, and then go a little bit, zoom out so you can see me again. So yeah, that's very nice, guys. So now we know what is K and how K depends on L, the length of the array of atoms, and also we know how K depends on N, and N here, guys, can be a number. It is a constant quantum number. It can be 0, plus minus 1, plus minus 2, etc., and plus minus 3. Now what I'm going to do, guys, I'm going to move to the other side right here, and I will focus a little bit like this. Maybe I move to this side. Okay, and then focus a little bit more. Yes, that is very nice. I will now move this a little bit up so you can see what do we have here, guys. So what I have here, guys, so again, for Bloch wave function, and I'm sorry, this is a typo, it should be O. So for Bloch wave function, we know, guys, that psi in K as a function of X. We proved that, if you still remember, in my previous session, even though I didn't finish the session, but I just included the last part, guys, in my note. I sent you that note. So you can see that Bloch wave function. Maybe I need to go a little bit back so you can see me speaking here. So psi in K as a function of X is equal to C in K exponential I kx u in k as a function of x. So this is Bloch wave function. Now guys, since this is very important, so here you can see that since u in k as a function of x is periodic over the unit cell, as I mentioned guys, so that means u in k as a function of x plus a actually is equal to u in k as a function of x. This is the periodic wave function. So then what will happen, then we normalize, I will go down, so then what will happen, so then guys we normalize, so let's go down like this. So then we normalize u in k as a function of x over the unit cell, and then apply the periodic boundary condition. Okay, apply the periodic boundary condition inside nk, so that will give me the following guys. This is very important for you to know. So I will move this a little bit down. So that means psi nk as a function of x plus L, and this L here guys, we know that L is equal to NA. N can be 1, 2, 3, 4, 5, or we can consider N here. So instead of having A here, we can have L, which is N times A. So that is very nice, and that's equal to psi nk as a function of x, where Na is equal to L. So this is the condition of a periodic boundary. This is actually how to apply the periodic boundary condition. And you can see guys, now the wave function actually is equal to exponential ikl now. It's equal to exponential ikl, and that's actually is equal to L. So that's very nice. We know that guys, that KL is equal to 2 pi times n. This is what we know. And n is equal to 0, plus minus 1, plus minus 2, and etc., and plus minus 3. Again guys, if you try to focus in what we have from Bloch wave function, you will see that we got the same thing that we got from the free electron case. So you can see that KL is equal to 2 pi n, and I will give you again K is equal 2 pi n over L, or K is equal to 2 pi n over Na. So the same thing that we got from the free electron problem. So there is no big difference here guys. Okay, just application so you understand guys how can we deal with a Bloch wave function. So this is a very important to know. And also guys, we don't have enough time actually to finish chapter 8, but I'm doing my best right now just to give you the main topics, similar to what we have right here. How can we work with the Bloch wave function and apply the boundary condition for the system that I showed you right here, this system of atoms that you can see, the one-dimensional system of atoms. So that is very nice. What if we now guys try to jump to another very important thing? So I will move now here and try to catch everything with the camera, and try here guys. Okay, so we mentioned that K is equal to 2 pi n over L, or 2 pi n over Na. That means we have K is equal to 2 pi over A times n over capital N. N here is a number, and capital N here actually represent the number of ions or atoms in the unit cell. In the lattice. Okay? N is equal to 0, plus minus 1, plus minus 2, and etc. So when n is equal to minus n over 2 to n is equal to n over 2 minus 1, so that will give me very, very important thing. So what is that? So that will give me, guys, the Brillouin zone. Okay? Completely Brillouin zone. And that Brillouin zone, guys, will be determined by two k numbers, which are minus pi over a and pi over a. If you try to apply that here, guys, so maybe I will try to write that down here for you and show you how can we have minus pi over 2 and pi over 2. So let's apply that and see what will happen. Maybe I will write that down right here. So yeah, let's see that. Okay, so this is a very, very important topic, and I advise you guys to start preparing for the final. So yeah, so we know that k is equal to 2 pi over a times n over n, and I will now apply that. So I will have now n is equal to minus n over 2 and see what will happen. So k in this case is equal to 2 pi over a times minus n over 2n. So n will be cancelled with n and 2 will be cancelled with 2, so that will give me minus pi over a, and this is the first k value that we mentioned. And after that, guys, I will go back to this figure again and talk about the energy levels. It is very important. Now I will move to the other k value. So we have 2 pi over a, and what do we have here? We have n over 2 minus 1 divided by n. Okay, so this is actually is equal to 2 pi over a. So maybe I need to go a little bit back so you see what I'm doing, and go a little bit down, focus, and go a little bit down. Perfect. So I have 2 pi over a, and 2 n over 2 divided by n, so that will give me here 1/2, minus here we have 1 over n. So n here, guys, can be a huge number. It can be very, very large number. If n is very large number, so the whole thing here actually is equal to 0, and you will see the result, guys, is pi over a. So you can see, guys, these are the k values. These are the k values, so we have minus pi over a and we have pi over a. So that is very nice. Let's now, guys, after we did this, it is very, very nice idea to try to finish what we started right here. Okay, so we mentioned that the k values can be from a pi over a, or from minus pi over a to pi over a. So that actually, guys, can give us the k region that can include Brillouin zone. And actually this is called Brillouin zone itself. Okay, so I will go down right here, guys, and show you this very nice figure. So this is a very nice figure, guys. So as you can see right here, so what do we have? So here, guys, we have an array of atoms, as you can see. These atoms, guys, are between minus pi over a and pi over a. Actually here I'm using k space, just using k space. These can be considered as points as well. You don't need to consider them as atoms. So these can be considered as points. When n, which is this number right here, guys, is very, very large, so what will happen here? This n, when n is very large, guys, which is indicated here, when n is very large, so that, guys, or this system that we have right here can be called quasi-continuous system. Quasi-continuous system when n is very large. But when n is very small, so you can see that we have discrete system again. This number n, guys, also can be considered as a number of states. So you can call the number of states by n. So that's possible. Okay, and you can use this equation, guys, to calculate k. So number of k values actually are n is equal to the number of unit cells over the periodic boundary condition. Okay, so this is very important. So number of k values actually are n, and in here is the number of unit cells over the periodic boundary condition. So that is very nice. This is what will happen in k space, and I will go back, guys, to talk about the energy levels again, and maybe I need, guys, here to change the camera direction, and maybe I need to do something here. So I know that the computer prevents you from seeing what we have in this whiteboard. So what I'm going to do here, I'm going to move this. Okay, so maybe that can help you, guys. So maybe that can help you to see. So let's see here. That's very nice. So you can see all of that. So again, we have the array of these points, and these points, guys, can be close to each other. These points, guys, can be close. So go a little bit up. Yes. And these points that you can see right here can be close to each other when n is large. And when n is large, we can call what we have right here like quasi-continuous system, okay, in k space. Okay, and we have everything between pi over a to minus pi over a, and what we have in the middle actually is called Brillouin zone. So that's very nice. If I now go down and try to conclude what we studied for today, so we'll see, guys, that it can be applied to both electrons. So what we discussed right here, guys, can be applied on both electrons and phonons. And you can see, guys, that k plus vector g, that's equivalent to k again. So why is that? Because of periodicity. And actually that can be applied on Bloch wave function, which is psi in k. I think I need to include in here. So we have here n k as a function of x. So that's very, very important. Now, guys, we understand how to study a Bloch wave function and apply the boundary conditions, which is very, very important. The only thing that we need now to study actually is what we have right here, guys, again. So let's come to the light again. This is actually, guys, what do we need to study. So I will go closer and move the camera a little bit up. This is actually, guys, what do we need to study. This is what we have in k-space. And this is actually represent the plot of the dispersion relation. How can we have this this plot right here. And we agree, guys, that we have discrete energy levels. So if I try, guys, to plot that for you, so what we can do, I will have the ruler, just a minute, right here, and try to show you how can we plot this in K space first. Okay, let's do that. So we know that the vertical axis represents the energy, okay, and the horizontal axis right here represents K values. And this is actually called K space. So this is K space, guys. Okay? Also, statistical mechanics is included here. So this is K space that you can see right here. Okay? So now, and here we have the energy. So let's do that. I need to move this a little bit to this side and then go a little bit back. So you see what I try to draw for you guys. Okay, so this is the energy as a function of K. This is K right here, and we know that yeah, the energy is proportional to K squared. If I try to plot K, guys, so what kind of plot we will have? We will have parabola. As you can see right here, this is what we will have because E actually is proportional to K squared. But what will happen here, guys? The thing that can happen, I will try to draw this again. Maybe go like this. And for this one, I will try to go a little bit like this. So let's try to do that. I still have a hard time to have it drawn correctly, so I will do something like this, and then come here, and then do something like this. That looks perfect, guys. Okay? So that looks perfect. Here we have continuous energy levels. But if we try to come here and make some spaces, I will create the first space. So this is space number 1. And here we have space number 2. So you can see, guys, that we have something like this. Okay? So we have something like this, and you can see, guys, that there is a discrete energy levels now. There is a kind of gap here, so this is a gap, and also here we have a gap, and here we have a gap, and here we have a gap. So if we consider, guys, the first Brillouin zone, we consider that between minus a over 2, minus pi over a and plus pi over a. And what I'm going to do here, guys, I'm going to flip those two like this, because we have here periodicity. So there is a periodicity, since we have this property, and also by applying the boundary condition, so we can have something like this. We can flip this to the other side, so we can have something like this. So this portion represents this portion, and this portion right here represents that portion. What we have in the middle here actually called Brillouin zone, and it's between plus pi over a and minus pi over a. So there is a second Brilliant zone and there is third Brilliant zone, but we are not going to study that for now. So here we can have now E1 as a function of k, and here we can have E2 as a function of k. That's very nice. This is how can we draw the energy levels. So this is how can we draw the energy levels, guys, as you can see right here for this kind of system using Bloch wave function, and also by respecting the boundary condition that led us to know these two values, pi over a, or plus pi over a, and minus pi over a. So I know that today's session is short, so I apologize for that. I can't stand up for a long time, but I think we covered the majority of the topics that we need to cover for today. So that looks very nice. I would like to advise you guys to study for the final exam. The final exam will be take-home exam. I will give you 4 problems to work on, and the final exam, guys, will cover the chapters that we didn't do. Okay, so I believe chapter 7 and chapter 8, and also we didn't cover the whole thing in chapter 7. Okay, I will double check from Canvas and get back to you right now. So just wait, guys, and see here. If I go to Canvas and go to the syllabus, so here is the syllabus. So the final would cover chapter 7 and 8. So chapter 7 and 8, and I will not cover, guys, all of the topics here. Okay, we know that we covered some of chapter 7. We covered some of chapter 7 topics, and also we covered some of chapter 8 problems. I will double check chapter 6. I think we included chapter 6 in exam number 2. Crystal structure and X-ray diffraction. Yes, so that was included. That was included in chapter in exam number 2. Okay, so just study those 2 chapters. Use, guys, the recordings that I give you. Okay, so study them. Use my note if I send you any note related to these 2 chapters. So study that. You can use the book and just study the topics that we need for the final exam. So you have 2 chapters to study for the final exam. I will post 4 problems during the exam day. And the exam day, guys, according to Canvas, is December 13th at 4 p.m. So December 13th at 4 p.m. What I'm going to do, guys, I'm going to post these 4 problems December 13th at 7 a.m. and give you the whole day, guys, to work on these problems and then email me these problems back. Okay? This is what I will do, guys. So I can have enough time to grade your final exam and then post your final exam. And I wish you guys success for all of you. Okay? So we are done for today, and thank you so much.